Alright, so my name is Mohammed, and as in this video, I'm going to be talking about something very interesting that relates to physics, and that's going to be the topic of astrophysics. More specifically, I'm going to try going over the concept of a black hole and gravitation as a whole. So, if you're in Physics 1, as we all know, black holes and planets and just general planetary motion use basic Newtonian mechanics to describe them as a whole. However, there are some aspects to that concept that aren't as solid as they need to be. I'll evaluate more, and I'll actually explain the concept of a black hole, some common terms, and how we can use them in the real life and actually do calculations with them. So, I'll be talking about black. So I'll be talking about black holes and some of their properties. So first, let's start off with a general picture. So a black hole, normally speaking, is going to look something like this. And I'm going to try using a different color here. But so usually the way a black hole is even created is that you have a star, all right? And I know that's an ugly looking star. But this is just to illustrate my point. So we have a star, it's shiny, and when a star grows old, all right, with time, it starts to build up matter inside of it. The thing is, there's a balance between gravity flowing inward, all right, so this is gravity, G, because of its mass, and we have fusion, which is pushing it outward. So I'll denote fusion by F. So it's just coming from it out. And fusion produces energy. All right, it's pushing outward per se, and gravity, because of the star's mass, is pushing it inward. So we have a balance between G and between F. So G is equal to F. But however, with time, fusion can be a little tricky. Because what fusion does is we have particles of hydrogen being converted to helium. So H, oh, my bad. So H goes to He, and we actually have a buildup of elements because of atomic collisions, and that goes into nuclear physics. I won't go too much into it, but basically, you have this conversion of elements, and eventually, you go from helium and you keep building up elements until you get to a solid, and that solid is going to be iron. Now, the thing is, gravity's still pulling in, right? I mean, you're not really changing the mass as much. But the thing is, when you have iron, it can't really convert to another element. It's obsolete. It's not a gas like hydrogen or helium and oxygen and all those elements that come before iron. And that's when the issue arises. And you have a star, and so let me draw a new picture. So you have a star. Oh, yes, good circle. So you have a star with all this iron. Okay, so that's our iron. And then we have the rest of the, so this is everything out here is the rest of the star. But we have our, and I'll use the same color, so we have our hydrogen and helium here. And so that's where the issue arises. Because gravity now is going to overpower the fusion. The fusion can't occur anymore. So actually now we have this relationship where the fusion generated by the star is less than gravity. And so you have this huge amount of gravitation force to this mass. And of course that's a bad thing because now that you have no more fusion, this force of gravity is going to overpower the star. And the star will collapse into a black hole. And of course, this is not, let me just erase this. My mouse is not working, but that's aside from the point. So now you have basically this particle, and let me choose a good color here. So now you have a much, much smaller circle or star, and it keeps getting smaller and smaller until it collapses into what we know as a black hole. So now it reaches a point, and this point is called the singularity. And you can admire my handwriting here, but now that this point, that the star has condensed to a point, we have a singularity, and that singularity is a part of the black hole. Now, you might be wondering, well, Muhammad, I usually hear facts about neutron stars, or I hear something about, you know, not all stars, really turn to a black hole. And that's true, all right? For example, if you have a small star in this example, there are two ways for this to go about. And I should have probably written this earlier, but these stars can go into something called neutron stars. All right. And these neutron stars, oh no. Okay. This is really annoying, but you get the point. Oh wow. Okay. So you go and they become neutron stars. And that's usually the case where this happens is usually with smaller stars that aren't as massive as some supernovas. And that's the thing. If you have a big enough star, it will condense to a point into a singularity. But before that singularity occurs, we have something interesting happening. We have a supernova explosion. And it is this huge explosion, all right, that generates a massive amount of energy before the death of a star. And then that's what yields the singularity. Now, at this singularity, you have this huge condensed amount of mass. Okay, and in fact, the rate at which this supernova or the previous star condenses to a singularity is so fast it goes nearly a quarter of the speed of light. All right, because if you think about it, if all this matter is being condensed to a point, that means the gravitational force will increase, right? Because the radius is decreased. All right, so that's from our basic m1 times m2 over r squared. But that's going to make the force even larger, so it'll even go faster, and so it basically loops, all right? It loops into an infinite cycle of condensing matter, and that, my friends, is how the black hole is created. So now we have this big chunk, and in fact, I should probably, so yeah, so we have this big chunk of mass, and some terms. So that what's inside the black hole is called the event horizon. So this is, oh boy. See, this is just not cooperating with me today. So this is the event horizon. Okay, and now as you might know already, black holes suck in light. Okay, they're so massive, their force of gravity is so strong that even light can't escape it. That's why we usually don't see anything inside of it, where we don't see particles or whatever might be inside of it. And at the very, very end of a black hole, we have a point. And again, that's our singularity where we were talking about. Now, here comes the interesting part though. What happens in a black hole? I mean, really, what is it? So let me draw a 3D model here. Let me use the color red here to just illustrate my point. So this is our black hole here. So we have it's kind of the outer rim. And then we have our condensed matter here. And this kind of looks like a cone, but you get the point. So that is our singularity. Oh boy. Singularity. Okay, and typically light can't escape from it, or in fact, you would have to technically be traveling faster than the speed of light to be to be in the event horizon. And so there, what's really amazing about black holes is some of their properties. So, and I'm just going to clarify a common misconception. So, when you put a black hole in a system of planets, all right, so you have, so let's say this is a ring of planets, and we have our sun in the center. If you replace that black hole with the sun, there's not going to be a difference, all right? It's still going to be the same. My point is, the farther away from the singularity you are, the less effect the black hole will really have. So in fact, if you actually replace the black hole with the star in the center, not much is really going to change. Now, another interesting thing about black holes is their immense power of gravity, all right? In fact, we really don't, what's really interesting is we don't know, even physicists today, we have no idea what happens at the singularity. Who knows? It could be some new form of matter. There's just not really too much information that we have at the moment. What we do know, though, is that black holes will eventually die. And this is explained by the process of Hawking radiation. So, let me see if I can. Okay. So, Hawking radiation essentially states that is a theorem or theory by Stephen Hawking that states the following. So here's our black hole, and we have these little particles. Okay, so imagine we have one positive particle and one negative particle that form into existence. So that's our negative, and this is our positive. But when these particles come to existence, they will eventually merge and create nothing in the end. But with a black hole, as I already stated, the gravity is so strong that some of these negative particles are going to come into the black hole, and what they're going to do is they're going to be sucked in. Okay, they're actually going to go away. Normally they go towards each other, but they're going to go away. These positive ones are going to be left with nothing, and so they're going to go away. So these negative particles are going to come in, and what they do is they decrease the size of the black hole. Now, if you want to actually understand why, well, that's going to take, well, that's kind of going into relativity. And obviously, I mean, we're only high school students, so I don't think that we could really go into the actual mathematics behind that. But later I'll show you some math that can be applied to this. But anyways, so these negative particles condense the black hole. And what's interesting is that the temperature of the black hole eventually increases. And as it gets smaller, the temperature even increases even further. Okay? So, and then what's interesting is the temperature will eventually reach something of a billion nuclear warheads equivalent. And so at the end, and now obviously this is a very long process. This will take millions and billions of years to actually occur, depending on the size of the black hole. But as I just thought that was a very interesting property as well. Now, what's interesting about black holes is we don't know much about them. All right, we're still continuously researching. We don't even know how they look like. You usually see artist renditions, all right, of these really large, we have these seismic um, here. Let me pull up something. So this is just an example of a picture that most is a rendition of what most people might think a black hole might look like. We actually don't know what's in that center. All right, and this is just I think this is just they're just showing an example of a black hole usually at the center of a galaxy here, but obviously we don't really know how they look like. For a uniform sphere to a point, and this is where the math kind of helps us kind of talk about black holes. So black holes aren't uniform in density. As I've already mentioned, the singularity is a very condensed piece of mass. Now, actually, what that is unknown to scientists, but we can kind of generalize a few things if we know a uniform sphere of uniform density. And the reason I want to talk about this is what we do know about gravity as a whole and how we can talk about and how when we're talking about planets and stars and everything we were learning in that gravitation unit in Physics 1, how we can generalize a lot of our concepts that we learned to under the assumption. And what assumption am I talking about? Well, the assumption that if we have a uniform mass, having a point where essentially you have gravity being the same as if you were talking about the outer edge. So I'm going to start out with something really simple. So we're going to do Fg equals, is equal to the gravitation constant times m1 times m2 all over r squared. And we're going to include something called the unit vector times r. And this essentially just dictates the direction of gravity. But it's kind of not helpful. We don't really include it because we know gravity is always an attractive force, not like an electrostatic force where it could be repulsive. So, here's the thing. When we use this formula, we always assume that we're talking about a point mass and its attraction to another point mass. However, if we're not talking about a point mass, we have to do something called integration. Okay, so the reason why we use integration is pretty simple. It's because we don't have that uniform mass. And so basically you have to sum up all the areas or all the densities, all the masses into one point. And you have to sum all of that to get a general formula for that varied point. Okay, so when we're talking about our radius, so this would be our radius, I guess, and I should probably label this as capital R. But when we're talking about our radius, now that we're not using a uniform point, we have to go to the third dimension. So normally, if we're talking about the third dimension, if we have because the density is varied, we're going to have, or not a point mass, I'm sorry. If density wasn't varied, that'd be a crazy problem, but so this is our z coordinate, and this is our x, that is our y. Okay, so this basically means now that we have to include our radius. So our radius, we're going to say, I don't know, let's say it goes from the center to outward. Okay, and that's our new r. And we have an angle of theta with respect from the horizontal of z. So now what we could do is we can now change our formula for gravity. And what we can do is we can include gravity in the z direction. Okay, So before we do anything though, and this kind of relates to um, rotational inertia and deriving it, what we're going to do now is we have our density function. And density we know is mass over volume. However, when we're talking about 3D coordinates, what we really have, and I'm going to simplify this, we have delta M is equal to x, y, oh no, let's see, y, z times, and that's not absolute value, times our delta V times our density. So this simplifies things a bit because our mass is varied. And the reason why we included x, y, and z is because of our varied volume. Okay, we're talking about a sphere here. And so we're looking at the x, the y, and the z. So that's why we have those coordinates included. And our density is uniform, obviously. All right. So now, let's return to our original formula. So now we can write here. Okay, I'll use this color. F of z. So the reason why we're including the z direction, now we're going to talk about the force of gravity on the z direction. Okay, because our mass is going to be changed. So, and also, if we're looking in the z direction, because in the x and y direction, we know that's just going to be a circle. But if our density has a level to it, or our mass has a level to it, okay, that's kind of rising up from that circle, we have to look at the z direction. And the way we do that is we have to look at how that angle relates to that z direction, all right? This is our radius from another object. So what we do is we take the cosine of that angle. So we have g, our constant g, that's always going to be constant, times the cosine of that angle all over. Well, now we have our radius, r squared. And the reason, again, we're taking the cosine is because, well, here, let me write this. This will probably make more sense. So based on this formula, we had our delta m before in the previous equation. I'm just substituting that in for the cosine and the delta v and the density. So our delta m, originally this doesn't have the cosine. Originally this is just g times delta m all over big R squared. Okay, our delta m, we knew because we wrote this as uniform density, that's a known variable. We can solve for that and we can plug these values in. We take the cosine of theta because we want only those values. It has to do with dot product, all right? Because that cosine theta is kind of derived from that unit vector r. Okay, I know this is a little, I know this might sound pretty new to most of you, but just stick with me, all right? We're gonna discover something really cool. So what we now have is, well, delta G times our uniform density, all right, times our delta V. Okay. Now, and R squared is, well, R squared. So that's not gonna change at all. Times the Okay, so now this is where it gets interesting. We need to be able to find, so let's start from our original formula we just wrote a couple seconds ago. So delta Fz, so Fc, our force in the z direction, is equal to, I know that looks like an S, but just bear with my smart pad I'm using right now, times the density, times the volume, times the cosine theta. Again, that's purely because we're talking about dot product and direction, all right? That's pretty irrelevant. All over R squared. Okay. We have something in the z direction. Okay, and this is where it starts getting crazy. When you have acceleration versus time, if you take the area under that, oh, I'm sorry. take the area under that, you will get velocity. If you take the area under velocity, you get delta x. Similarly, if we have our z function, all right, this is just the third component. We integrate that, we get our xz or our yz. Okay, either way, you'll still get the same result. You take the area under that, you'll get our x, your y, and your z. So that's exactly what we're going to do. We're going to take the area 3 times, and we'll be able to convert all of this information into x's, y's, and z's so that we can write a general statement about the gravity of a uniform density sphere, and how that relationship relates to a point mass, all right, compared to inside the sphere and outside the sphere. And we'll be using that information. We can say something very cool about that information, all right? This will all make more sense in the end. Once you see the end result, this will make a lot more sense. But just bear with me at the moment. Okay, here we go. So we have Fz is equal to, well, this is where it gets interesting, okay? We have equals g times the triple integral. Okay, calm down. I know. This all sounds crazy, but it's intuitive. Okay, so that's to the cosine, so we still have pretty much the exact same thing, except our cosine, and no, yeah, we still have the same thing. R squared times delta V times the density. So this is all still the same. Nothing changed. We're not doing anything crazy. What? Okay, so using a bunch of math, we're gonna get this new formula, okay? So just bear with me. So we're gonna have this. We get the following. F of z, oh boy, come on. F of z is equal to g times, and I'm writing this really slowly, times 0 to 2 pi. Now, I know you might be wondering, where did I get this? Just please bear with me. I know. This all looks kind of weird, but so you'll get, so that's, and you'll get an A cosine theta, an A root 2 times, well, our sine theta cosine theta dp d theta. Okay, you might be wondering, where did I get all this junk? Well, here's the thing. You don't need to know how we got this. What you do need to understand is how the concept of where we got this. Again, as I told you, take the area under one thing, you go up a dimension. Now we're at our x, y's, and z's. And this is actually how Newton derived it. Okay, so I'm just trying to do my best to explain how this would work. So when you actually compute this value, you'll get a numerical answer. That final answer is going to be our amazing result. And this will tell us something very interesting about gravity. You get 2 pi times big G times small a, and a is a little, it's a constant, okay. Or actually, a, I don't know. A is it's a vector component. Let's just say that. Times 3 root 2 all over 4 minus 1. No. Okay, that's our final answer. So, what does this statement say? What's so interesting about going back to our original question? If you have a point mass and a big sphere, what does this thing say? Well, where did it happen to our delta V? That's gone. What happened to our m, our value for mass? Well, that's gone too. So what this shocking statement says, for some constant a, all right, it's a vector component. For some constant a of a uniform solid sphere with uniform density and some mass, all right, because we had that delta m in the beginning. If you have those conditions set, that sphere is going to exert a gravity just the same as if you treated that sphere as a point mass. So if you had a sphere, a hollow sphere of 1,000,000,000 miles, and you had that sphere condensed to a point and treated it just like the original sphere, you would get the same value for gravity no matter what. All right, and this is a very important thing to realize, because back to our black hole argument, remember what we said. We were talking about the singularity, a single point. And we talked about how gravity varied. So my point here is that with our solid uniform sphere, we can make a huge number of assumptions. This is why we are able to assume with planets and gravity, yes, I know, you have to include the value of r, to the center, but that's not my point though. We're able to treat planets, all right? The whole reason in physics why we are able to treat solid uniform spheres as point particles when we're doing rotational, when we're doing all these physics, is because of this. This is actually a calculation done by Newton, and he discovered that, hey, if you have a sphere, solid sphere with uniform density, and you put an object, a duck, okay, you put a duck here, and you close that sphere and put it to a point, it will exert the same force on that duck, even if you treat it as a point. And that makes calculations so much easier. You don't have to go through this whole proof over and over again. It just makes calculations easier. Okay, if you placed that point mass, this animal here, this boat, train, all right, a monkey, you place that point mass even in the center of it, it's still gonna be the same. And that's really shocking, because if we look back at our black hole argument, our singularity, remember, what's a point? Sure, this is not uniform density at all, all right? You might even argue that the whole density is here. I get that. But it just provides a much more unique insight to how gravity varies and just how powerful black holes are. I mean, the density is so varied within a black hole to the point where you can essentially treat as if all of its mass is at a point. Sure, the density isn't uniform, and obviously you're going to need graduate level physics to actually find that, right, a formula for all that gravity, but it's kind of the same concept. And I really hope that when next time you do a planetary motion problem, it really makes sense.